Hello and welcome to this manufacturing process technology part 1 module 6. We were talking about Czochralski's growth method for getting single crystalline silicon, and we had mentioned about the one dimensional heat transfer case which is analyzed here, right here. You can see here that there is a crucible, there is a vacuum chamber which is filled with, first of all evacuated and filled with argon gas, and then there is a crucible which is heated from the walls, and there is polysilicon or poly which is actually 99.99% pure present here in the core of the hearth, and the hearth is heated up so that there is a liquid silicon, and then there is a controlled lowering of a seed crystal which is chemically polished and which would give or provide the directions, and then as the vacuum chamber rotates and the crucible rotates and also in the opposite direction the seed rotates, you basically change the rotations for both and try to make a larger or a smaller bowl of silicon, which is obtained by pulling out the seed so that it goes suddenly into a solidification zone. And so this is the zone of fusion or zone of solidification that you may refer to, where there is a heat transfer taking place at a certain rate from the temperature T1, which is at a much higher value than the temperature T2, which is the ambient. This is T2 and this right here is T1, and so basically there is again a heat outflow Q2 dot x which takes place across this other boundary here, and based on that we had actually formulated these heat rates, and we had taken this from the Fourier law of cooling or heat transfer, which talks about the proportionality of the heat rate to the negative temperature gradient and also the thermal conductivity of the medium which is in question. So here from one side the thermal conductivity property that would be utilized would be that of the melt or the liquid, because the heat is emanating from the liquid side into the zone of fusion, and on the other side the heat is emanating out. So basically the case is that of the solid silicon which is formulated. So this part is the solid silicon, as you can see the solid phase, this is the zone of solidification, this is the liquid phase. So this is really Q1 dot x and this is really Q2 dot x. So obviously the Fourier's law can be written in terms of the thermal conductivity of the liquid times of area of interface times of the temperature gradient across the liquid phase to the zone of fusion, and for subsequently for the solid phase. So this heat which is released by the in the form of heat conduction across the liquid to solid transition also accounts for the bond formulation process, because obviously more heat will be pumped from this side into the zone of fusion, but less heat would be pumped out. So the total amount of heat accumulated in the zone of fusion is really the difference of the heat inflow minus the heat outflow, and that heat is converted into the bond energy because there is a formulation of the solid. And let us say the rate at which the formulation of solid mass takes place, if we consider that to be dm by dt, then L times of dm by dt, where L is the latent heat per unit mass, is basically the heat rate that is getting lost into the zone of fusion by virtue of the solid bonding formulating because of change in temperature. So then it is left to a very reasonable approximation where we can convert this dm by dt as basically the area of interface times of the density times of the upward pull rate dx by dt of this particular seed crystal. So it is moving at dx by dt. So that is the only variation in time which is happening. We assume the interfacial area, the zone of fusion, be constant, and the density also does not vary much. So therefore from the zone of fusion into the solid zone. Okay. So therefore if we just solve this equation, it comes to have a form L rho dx by dt equals kx dt by dx in the solid phase minus kl dt by dx in the liquid phase. Area gets cancelled off, and obviously the maximum pull rate that can be obtained is a condition where mathematically this part of the right hand side goes to 0. Okay. So if we assume that the total amount of latent heat that is lost within the system is the heat that is extracted out. Okay. And so, you can write down this maximum pull rate dx by dt as Ks by L rho dt by dx s. Okay. So, let us just rewrite this here as V max, the maximum pull velocity of the seed crystal dx by dt, which you can now write as Ks by rho L dt by dx of the solid side. So, obviously, the maximum pull out rate or dx by dt therefore, is proportional to the dt by dx of the solid, meaning thereby that if I increase the temperature gradient in the zone of fusion to solid transition, obviously more is this gradient, the more would be the pull rate, or in order to for the heat balance or for the heat optimum balance to take place, the pull out can be increased, okay, with the temperature gradient. But in reality, the maximum pull rate is really not the one which is used normally, and one of the reasons is the crystalline quality, which is a sensitive function of the pull rate. Okay. So, on one hand, if the material is near the melt, it has a very high density of point defects, and if supposing if we are quickly cooling the material, then there is it will really prevent these defects to go into formulating the crystal. However, too much gradient on the other hand may create a problem of thermal warping, okay, or thermal stresses, large thermal stresses within the crystal material. So, on one hand we are trying to make the pull rate little slower, so that faster, so that the point defects may not be enabled to get into the system. On one hand, we are saying that if the pull rate, which depends on the dt by dx, if the dt by dx is very high, then there are going to be thermal stresses. Okay. So, there are going to be dislocations or defects by just by virtue of thermal stresses. So, it is a trade off, So, in one so you have to really have an optimum balance, where without including the point defects in the silicon melt to go into the crystal, you should also be able to ensure that the thermal stresses are by and large neutralized, or they are not present, and the gradient is not too much overshoot. So, that is the trade off that silicon industry has to play in order to get a single crystalline silicon. The other method that is very commonly used is a float zone, which is used normally for a smaller wafer, and here the method is a little different, because here the rod of high purity polycrystalline material is held in a chuck, while a metal coil driven by a high power radio frequency signal is slowly passed along its length. So, it is basically a non contact mode of heating, and there are not many thermal stresses or thermal gradients. By and large, because of eddy currents, the material heats uniformly, and so alternately you can actually reduce this to a focused E beam also, that can also do the job of heating the rod. But the idea is that a crystal is lowered from this end, from the top end, as you can see here, and this crystal is the one which causes the growth to happen. And so, whatever liquid is created in this area because of heating, and the rod is being fed inside. So, the liquid would ooze out from here and fill up this, and this would be a melt, and the seed crystal, what is coming out in this particular area, you are pulling out. So, that the same constitution as the Zokralkes, only thing is the heating here is not a wall mediated heating, but a uniform heating of the material. So, in this technique, a thin neck of 3 millimeter diameter and about 10 to 20 millimeter long is pulled, and the pull rate and the temperature lowered to shoulder the crystal out to a larger diameter. So, that is how you can actually get this kind of a larger diameter constitution, even though the oozing out is only through a small orifice or a small cavity. So, you can't really go for a very big size here, because there would be issues related to incomplete supply of the fluid or extremely slow pull rate, which would determine the overall size of the crystal, etc. So, that is another way of growing single crystalline silicon. So, I would now come to the crystal imperfections, and as you probably are aware that some of the properties of the crystalline solid, they really depend on the crystal structure, and thus they should vary a lot based on imperfections in such structure. So, the study of crystal imperfections and their effects on the properties of a material is really a very wide domain of research or study, where with various properties, including let us say the mechanical properties, the electrical properties, so on and so forth, depend on these defects. And I am just showing you a small table here which talks about what are the properties which are dependent on the basic crystal structure vis-a-vis what is the property dependent on the crystal imperfection. So, on one hand it is the structure which is determinant, on the other hand it is the defect or the imperfection which is determinant. So, for example, property like density would depend on the crystal structure, specific heat, coefficient of thermal expansion, melting point, elastic constants, hardness and ductility. These are some things which are structure dependent. On the other hand, if you look at properties like electrical conductivity, they are definitely going to be dependent on crystal imperfection. Think about it, you are having a doping material like a group 3 or a group 5 material into silicon and changes the properties, electrical properties of the silicon, makes n type in one case, if it is a group 5 makes p type in the other case if it is a group 3. Okay. So, a small amount of imperfection of this material may change the electrical property considerably. Yield stress, for example, creep, fracture strength, semiconductivity, work hardening, fatigue strength, these are some of the properties which are utilized by change in the crystal imperfection. So, if we look at how or what kind of classifications we can give to the crystal imperfections, really there are 3 different kind of defects which are important. One of them is called the point defect, okay, where as the name suggests the defect or the imperfection is about a single point. There can be a line defect where we are talking about several such arrays of points together to formulate a whole line, and then there can be a surface defect where across the whole surface it is some kind of a complete movement of the surface from the regular orientation within the crystal which may change the nature of the crystal. So, let us look at these individual defects in a more classified manner. So, point defects, for example, they can also be subclassified into different point defects. One is where the atom can miss the regular site, another is where the atom can be of a different constituent of occupying the normal atom of a particular site, and the third is that where let us say within the interstitial spaces where there was supposed to be no atoms in the regular arrangement of the crystal, there is an impurity which gets plugged in. Okay. So, based on this the point defects are classified into vacancies. Obviously, as the name suggests that vacancy is a site which is created because an otherwise regular atom has moved out. You can see this particular figure here, there was an atom which was supposed to be there, but it has moved out, and so this creates a vacancy. The other is interstitial impurity, where the interstices, that means the site where the atom is not supposed to be present, there is some kind of a atom of the same kind or of a different kind present in such an interstice, which actually relates to a bulging out of the crystal, a change in the shape and size of the crystal, and that can be a very pertinent cause of mechanical change in mechanical properties because of the induction of such a defect in the crystal. It has basically made the crystal to already be pre-stressed from its regular orientation. And then there is substitutional impurity, which means that any regular site of the atom is replaced by a different material altogether. It is not the same atom that is substituting, but different atom which is substituting the regular site locations. So, that is how you classify the defects as vacancies, the point defects as vacancies, interstitial impurities and substitutional impurities. How they formulate, what is the usual order of the vacancy. So, at about 500 degrees Celsius, for example, it can be about 1 in 10 to the power of 10, and it increases to 1 in 300 at about 2000 degrees Celsius if we talk about a certain particular lattice. So, it is possible to increase the vacancy density at a given temperature by rapid cooling or extensive plastic deformation. Okay. So, that is how you create the point defects. Then there are line defects. Now, as the name suggests, there are more than one points which are in an array and like a line, and that moves. So, here you can see, for example, two different kind of such line defects, edge dislocation and screw dislocation. For example, there is a complete line across many such points together which comes up, and there is, because of this line, an additional plane. So, if you look at this particular lattice from varying from here to here, there is an extra plane x dash y dash x y, an additional plane which has come up here for having a edge dislocation. So, whenever there is a mechanical work which is done on this particular lattice, there is a movement of this extra plane, okay, which leads to probably a quicker response of the crystal to a mechanical deformation. Okay. So, this is called a edge dislocation. So, the dislocations can also be that instead of pumping an additional plane of atom, if I really try to shear apart or tear apart by few paces, by few atomic units, the crystal can look something like this, which is called screw dislocation. You can see that one part of the crystal, this part has been sort of in shear with respect to the other part, and there is one plane movement, okay, of one part with respect to the other based on that. So, that is a screw dislocation. Okay. So, the dislocation density is something that is a very important term here. So, you can say that it is the total length of all dislocation lines per unit volume, and so if in this particular case, if I had let us say 50 nanometer line defects, about 50 numbers, and in about maybe 1 centimeter cube of the material. So, you can think of how would be this dislocation density. So, you have about 2500 nanometers 10 to the power of let us say -9 per centimeter cube, which makes it 10 to the power of -6 meter cube, and 100 centimeter makes a meter. And so, therefore, you can think of the dislocation density by virtue of only 50 nanometer lines in a 1 centimeter cube volume of crystal to be as high as 2.5 per centimeter or per meter square. Okay. So, that is how you can actually calculate the dislocation density. So, typically in a crystal, the minimum attainable dislocation density is of the order of about 100 to 1000 per centimeter square. This, if I convert into centimeter square, would be in the range of 2.5 times of 10 to the power of 4 centimeter square. So, that is 2.5 10 to the power of -4 per centimeter square. So, you can think of it that the actual attainable dislocation density is of the order of 100 to 1000, which is about 10 to the power of 6 times this value. So, there are definitely maximum most of the lattice which is basically pre-stressed because of all these conditions, and that really gives a very wonderful insight into why such dislocations, or because of these dislocations what is going to be the effect on the overall mechanical properties of the material. So, it so happens, as I am going to now do maybe in the next few slides, that the actual modulus of elasticity or the actual shear modulus, if you model it from a lattice viewpoint, and then if you try to see what happens because of dislocations, you will see that the moduluses are quite far apart, probably hundreds, probably 2 or 3 orders of magnitude apart. And one of the reasons is that when you are doing a pre-stressed lattice and trying to shear it or stress it, obviously the dislocations are going to help you out, okay, to do that. So, having said that, let us see the third different kind of imperfection which extends over a surface. So, the imperfection is known as a surface defect. For example, you can see here the lattice was moving in this direction, and suddenly because of a stress to this lattice, as can be applied from as can be seen by these arrows here, the plane has changed into an altogether different direction. And so, basically these results in the formulation of these two parallel discontinuities between the regular direction of the crystal either way, and these are known as twin planes or twin planes, and this imperfection is known as a surface defect. So, the figure below shows a common type of surface defect known as a twin, which are normally produced when the metal is stressed at low temperature. And you can see that the grain boundaries in a polycrystalline solid can also be considered as a sort of a surface defect, because here is where there is a discontinuity in the direction of the crystal. I had earlier mentioned that in a polycrystalline grain you have one direction in this particular manner, crystal growing in this direction, another direction maybe on another grain maybe in a different randomized direction, and so between those directions there are these discontinuities which exist, which are called grain boundaries. Okay. So, these grain boundaries are similar to the twin planes. That is how you can probably envision it, and you know, the difference that you can see from a external point of view, that is, let us say an object is stressed longitudinally, and so the way that twinning would happen would be represented here, where a permanent deformation of a single crystal under a tensile load acts or looks like this. You know, the slip planes tend to align themselves in the direction of the pulling force, so that there is generally a reduction in the cross sectional area as you pull the specimen. Okay. So, that is how you can envision that how twining helps in sort of overall longitudinal extension process. Okay. Whereas, this is a pure shear stress from which the atomic planes are dislocated with respect to each other. So, here we are talking about the formation of a slightly different zone with a different orientation of the crystal itself between those two guarded planes, which would try to angularly shift like a pack of cards and try to reduce the cross section of the material, as you can see here right in this example. So, that is how slip and twining can be defined. So, in a general polycrystalline material, you can have several of these slip surface slips which are happening, and you can see that here, for example, you have a band of such slippages which are together. So, these are all the different bands. You can see how it has deformed in a particular direction because of a shear stress, which is applied to this crystal in two anti-parallel directions on both sides. And you can see that the sort of slip lines that are generated here are about 100 atomic diameters in a regular polycrystalline material, and approximately the quantum of the slip in the shear direction that has happened is about 1000 atomic diameters. Okay. So, that is how you can generate the slip lines and slip bands. So, a sequence of such slip lines in a crystal, in a polycrystal, as you can see here, is normally known as a slip band. Okay. So, with this I would like to finish this module. In the next module we will see that how numerically the values can be calculated with the keeping the whole crystal structure in view, and then trying to pile up dislocations to see what are the actual values, and you will see what is the quantum of difference between the modulus of rigidity maybe as the presumptions shift to dislocation driven as opposed to pure crystalline. So, I am going to do that topic in the next module. As of now, goodbye.